I would like to thank the organizer of this very nice conference for the opportunity they are giving to me to present this research. So this is more or less the plan of the talk I would like to present. I will spend a lot of time in the motivations. So this is the last session, so we will be a bit more relaxed. So there will be also a nice historical part. Then I will say what I mean by regularized interaction Lagrangian and regularized theories. And then I will present some theorems about convergence of the S matrix for this regularized quantum field theory. And then we will discuss a little bit how one could remove the regularization when S introduces into the game. So, but let's start with the motivation. We are interested in studying quantum field theory, and we are interested in interacting quantum field theory. We know very well that there are nice experiments where with very high precision things can be measured, and in order to compare the theory with experiment, the theory side is a little bit behind because it is described with perturbative theories, with non-exact theories. So somehow the experiments are a little bit ahead of the theory. In this game, I am talking about the standard model. And so it would be nice to know in which kind of models it is possible to obtain rigorous interacting quantum field theories. And usually these are available only in very low dimension, 2 or maybe 3. And usually this is done for fields which are described on space-time, which are Euclidean. And what aim of this talk is to see if it is possible to use some of the ideas employed in the Euclidean construction of quantum field theory directly on a Lorentzian space-time. And in order to get some convergent S matrix, one has to use some regularization, and then we will try to see how it is possible to introduce this regularization and then to remove it. But let's start again introducing what I would like to talk about. So the kind of field theory I'm discussing is very simple. It's a Klein-Gordon field plus a nonlinear interaction. So this Li is the interaction Lagrangian of the game. And so the idea is that you can split the Lagrangian in 2 parts. There is a quadratic part plus an interaction. And usually this is what is done in perturbation theory. In order to get prediction, you usually try to construct the element of the interacting theory over the free one. And so the first step is introducing a adiabatic cutoff in front of the interaction Lagrangian. So we have this smeared interaction Lagrangians. And with this object, we would like to construct correlation function of the theory. So the time-ordered correlation function of the interacting theory are usually constructed over the free theory once you know the time-ordered exponential of your system. And there are, of course, many problems in the analysis of this kind of theories. There are some problems which are of ultraviolet nature. Somehow we try to multiply distribution in this game that cannot directly be multiplied. There are infrared problems in the game when we try to remove this adiabatic cutoff described by a compactly supported smooth function. We encounter usually divergences. And there are the most important issues, problem with convergence of the power series. So first of all, this theory is constructed as a formal power series in the coupling parameter, and one would like to understand if this series can be summed. We all know that nowadays, at least the ultraviolet problem are quite well understood. We understood with the theory of renormalization how to deal with them. Infrared problem can be also understood as sort of direct limits where you remove this smeared cutoff function G. And the real problem is the convergence of the power series. And a direct analysis of the convergence of this power series is simply not possible because we know there are arguments saying that this series you get in this case are just asymptotic series, so they cannot be summed. Nevertheless, we have developed in the last year, it has been developed a very nice framework which permits to treat the perturbative theory using algebraic ideas of algebraic quantum field theory, also on curved and flat backgrounds. But we would like to go beyond perturbation theory in this talk, so let's try to see what is available on the market. So a bit of historical analysis. What are the regularization we can use and what is known in the literature? So the people working in constructive quantum field theory, here there are some prominent names in this field, have worked a lot in this direction already, starting in the 60s, 70s, and 80s, and somehow, at least in low-dimensional theory and on Euclidean space-time, it is nowadays possible to construct some interacting field theories with polynomial interaction Lagrangian in 2D and 3D dimension, and it's also possible to construct models where the interaction Lagrangian is a bit more complicated, like in the Sine-Gordon model. Similarly, more recently, there is another approach that have been developed in the last year, and this is the approach coming from the community working in stochastic quantum field theory, the stochastic approach. So the idea is essentially this one. Instead of considering an Euclidean theory, one adds an artificial time to this Euclidean field theory, and the idea is that if you wait long enough in this Euclidean time in a sort of parabolic nonlinear theory with some white noise at the initial time, you end up in the limit t, this artificial time going to infinity, you end up with correlation of an interacting Euclidean quantum field theory. Prominent results in this direction are the one of Eirer and maybe other collaborators, Rubinelli and so on. There is another approach coming from the community working in many body fields, and this is mainly non-relativistic, and here the idea is essentially this one. Instead of considering a local non-linear or non-quadratic interaction Lagrangian, one essentially considers particles which interact through body potential. This V is the potential of this two-body force among particles, and from the quantum field theory point of view, this amounts to consider a Lagrangian essentially of this form. And clearly, one would like to construct the theory in this case, maybe some good states like the one describing equilibrium, and then eventually one would like to take this V to become a delta function. This is also a little bit problematic, but this is another approach that it is done in this case. But let's try to see another bit how this theory is constructed in the Euclidean space. I mean, the first element we've seen before. So the idea is that one wants to have a generating function of the correlation function, and this generating function of the correlation function is nothing but a path formally a path integral over the field configuration. And here you have the Hamiltonian of the system in the Euclidean game, and here you have a linear field. And so the idea is to turn this path integral into a real measure. And the nice thing is that if you split the Hamiltonian in two parts, quadratic Hamiltonian plus interaction Hamiltonian, again, the measure associated with the free part can be really computed. It is simply a Gaussian measure constructed with a known covariance of the theory. And the last step would be to compute integrals of this form, and so to get a measure also for the interacting theory. In order to do it, and this is one idea we will also use in our construction, is to regularize the covariance of the free theory, and this regularization should work both in the ultraviolet and infrared regime, and somehow this amounts to multiply with cutoffs of this form, the Fourier transform of the covariance of the theory. And the end of the game, if the interaction Hamiltonian this object here is bounded from below. The theory with the measure with regularized covariance can be constructed, and so what you have to check is to check what happens when you remove these cutoffs, and this works quite nicely in lower dimension and in Euclidean background. Now the idea would be to consider directly a Lorentzian quantum field theory, and this is usually done by analytic continuation. And we know that this is essentially using some Osterwalder-Schrader reconstruction theorem or construction. And in order to apply these results, as we have seen a few days ago, it's very important to control some analytic property of the correlation function of the Euclidean theory. And the most difficult problem probably is this reflection positivity, which is very hard to control in an Euclidean field theory. And furthermore, if usually we had this adiabatic cutoff into our interaction Lagrangian, and in order to do this analytic continuation, one has to take the adiabatic limit before doing the analytic continuation. This is also a difficult step to be done in this game. And furthermore, if we, instead of being on Minkowski, we would like to apply this method on generic background, everything becomes even more complicated. Nevertheless, at least in some two-dimensional model or three-dimensional one, the limit where this gamma goes to zero can really be taken. There is recently, it appeared recently on the market, another approach to interacting theory, which is more axiomatic. And this is the approach due to Buchholz and Fredenhagen. And so this approach works directly in a Lorentzian space-time. But now what people is doing is trying to construct the S matrix associated with this Lorentzian theory. And essentially one would like to give meaning to object of this form. And this is an axiomatic approach. So instead of constructing directly in these S matrices, they try to understand what are they understood, what are the relations that this formal objects needs to satisfy. And these relations are very, very small, like there are not very many. So there is a causal factorization property. These FBG are local functional, so they have a support. And it happens that when the future of the support of F do not intersect the past of the support of G, then a relation of this form needs to hold among these S matrices. So this is causal factorization property. Then there is the equation of motion, which is essentially written in this slightly complicated way, but this is nothing but an integrated Schwinger-Dyson equation that we usually know from the courses of quantum field theory. And there is a normalization condition, so a very economic set of axioms. And the interesting thing is that with this very economic set of axioms, one can generate a sister algebra, and at least an abstract sister algebra. So existence of the theory is guaranteed essentially, and what is lacking in this business is the construction of concrete realization of this algebra in states which are physically meaningful, like, for example, the vacuum or equilibrium state. So we would like to see if it is possible to have models where, at least in some regularized theories, this kind of S matrices can be constructed. Yes. And I am now ready to present you what are the regularization I am considering in the theory, and then I will tell you the result one can prove with this regularized theory. So we will fix our space-time to be Lorentzian, and we are considering fields over this space-time. Our aim is to construct the generating functions of the correlation function of the theory, and so we have an interaction Lagrangian, and we want to regularize it a little bit. So the first regularization we use is the standard one. It's just an adiabatic cutoff, which is used to remove at the beginning infrared problems. The second regularization is done to remove ultraviolet problem from the theory. So we add, again, we are constructing here a mean field theory. So this means we select a compactly supported smooth function on some Cauchy surface of our spacetime, and we construct with this approximation of the identities or approximation of the delta function, and we convolute this approximation with our field before computing the interaction Lagrangian. So this is a sort of mean field theory. This is used to control the ultraviolet problem of the game. In contrast to what it has been done in the Euclidean case, our mean field is essentially smeared only along the spatial direction. This is because we would like to keep meaning of the time order product, which are necessary to construct these S matrices. And for this reason, our field will be still sharp in time. And but these two ideas were already present in the market. What I am trying now to do is to add another regularization, and I will try to explain why I need this regularization in a while. So I will essentially tame the large values of the field in our Lagrangian density. So this Li is polynomial, but we add in front of this polynomial an object of this form. So this becomes a Schwartz function in the field. And since this becomes a Schwartz function of the field, we can now compute nicely Fourier transform of these objects. And so our interaction Lagrangian with all this regularization is essentially this form. So the field appear in this place as exponential of the field up to this ultraviolet smearing, this mean field smearing. There is a parameter A, and this F is nothing but the Fourier transform of this object here. And there are two parameters, lambda 1 and lambda 2, one which controls the ultraviolet cutoff, and the other one which controls the damping of the large values of the field. So it's quite nice here to have an interaction Lagrangian, which is essentially a sum of exponential of the field. This is the K observation, and this is the K object, which will be useful in order to construct these S matrices of our theory. And then essentially, we now construct time-ordered exponential of this interaction Lagrangian. This is again well-defined, thanks to the fact we have not smeared the field in time, and we get, first of all, a power series in the coupling constant we have into the theory. And now we would like to see if this power series can converge or not in some sense. And actually, we have these two results. So consider this interaction Lagrangian with these two cutoff. Suppose that one of these two is sufficiently small for technical reason, and then essentially the power series defined in this object, seen as function of overall possible field configuration, are absolutely convergent. And the estimates which guarantees the absolute convergence of this object are uniform in the field configuration. So it's still a weak version, a weak notion of convergence. Nevertheless, we can try to start with it to build something more under control. And in fact, if we now consider the GNS representation of the Minkowski vacuum, we are assuming to be in the Minkowski space-time, then again, the power series of the represented object can be shown to converge in the strong operator topology to a unitary operator. So we can turn this weak convergence done at the level of functional of very weak convergent notion into real unitary operator inside of the Hilbert space associated to the Minkowski vacuum. This works essentially up to a small condition on this lambda 1. This works essentially for all possible cutoffs you have into the game. And so now we can play with these cutoffs a little bit to see what happens. And what can we do? Essentially, we take all these objects. These are for all possible cutoffs. These are unitary element, unitary operator in the B of H of our theory. And then essentially, these are contained in the unit ball. And we know that the unit ball is complete with respect of the weak star topology. So if we select randomly a sequence inside of this set of unitary operators, we know that it's always possible to extract convergence subsequences. And so this is a very weak again, very weak notion of convergence, but it's there. So the idea is that we construct a subset of the unit ball, taking this n1 and n2 natural number, dividing the cutoff. So we try to reach the limit where n is equal to 0. In this procedure,
just to recall the setting. So when you do this limit, you get numbers. So these are functionals on phi, but the
idea is that you can
the product, no? Which is
of course the idea is that you use them in the product, and these are used to these are the aspects of the
limit works then in a product, and you can define the structure.
Okay. This is what one would like to have. But at the level, at this moment, we are still interested in understanding the S matrices. What are the object of these S matrices? And so what I wanted to say is that these limits are essentially non-unique. No? So if you select other subsequences, you get probably other limit points, so it's not clear what you have. So uniqueness is highly ruined by this abstract argument. It's a very abstract argument. Nevertheless,
you also have the cutoff with G, right?
yeah, the cutoff with G is kept. No, I think you cannot remove the cutoff with G so easily, because otherwise you would go against the Ag's theorem. So this is something I don't expect to be able to do so easily at this level. So in principle, you can work also with this cutoff, but probably only for expectation value of objects.
Yeah.
So when you compute expectation value of certain localized observables, then I think it's possible to compute similar things, but not at the level of S matrices.
Move the support of G independently of the cutoff value.
Yes, a little, yes. This you can. So, in some sense, I hope to have time to show you how in practice it works, but let me try to say what I want to say. So that these unitaries, as we lost uniqueness of this procedure in order to extract unitary operator, but nevertheless, we can try to see if at least we can consider or reconstruct sequences which are in accordance with perturbation theory. And this is what we can do. We can engineer a little bit this interaction Lagrangian in such a way that every convergent subsequent you extract agrees, the limit of this agrees with the prediction of perturbation theory. And this is done not in general, but only for lambda 4 in 3 dimensions. Okay, so it's still something, no? We don't have uniqueness of the limit point, but all this and maybe non-unique limit point agree with perturbation theory. So I was not relatively happy with this. Okay, and now I would like to give you some ideas on how this estimate works, because I think this could have some interest also for people interested in vertex operator algebras or these things. So let's see. So we start with the free theory, and now finally I have to tell you what are the objects we are really working with. The object we are working with are functional over off-shell field configuration. So we have, in the case of the scalar field, the field configuration we are considering are just a smooth function over our manifold, and we consider essentially all possible functional. Of course, we need to have some regularity for our functional. We need to be able to compute functional derivative. They need to have compact support, because usually our observable are compact support, and they must behave in a nice way in the ultraviolet game. So their functional derivatives must satisfy a certain microcausal relation. So it's a technical point. Nevertheless, relevant objects which are present in these things are the Wick monomials, for example, which are objects of this form. This is very simple. G is a compactly supported smooth function. Phi is the square of the field, and so on and so forth. Then other interesting objects are what I call the Weil operators. So there's an exponential of integrated fields. And furthermore, for our purpose, it will be also important to consider vertex operator, which are objects of this form. Essentially, we compute here, essentially we integrate the linear field against this test function before exponentiating, and here we exponentiate before integrating. And usually multiplication of this object themselves are more singular than multiplication of this other. And now the product among these things is this one, at least if I consider polynomial field, so only these objects here inserted in this one, then a product of this form is the one which we'll use. And this product encodes the properties of the quantum theory we are considering. And this is given in terms of the two-point function with a chosen two-point function of the free theory we are considering. And this two-point function must have an obvious property. So this is the two-point function of the free theory. Its antisymmetric part must agree with the canonical commutational relation of the theory. Its symmetric part must be real. And furthermore, we have to assume that the symmetric part is chosen in such a way the Hadamard property of this two-point function is satisfied. The Hadamard property is a weak notion of positivity, of frequency energy positivity condition, and it is spelled out in terms of the wavefront set of the two-point function. And if I have one of these Hadamard states, essentially I can construct this becomes a star algebra if the polynomial subset of this functional with this product and with star involution becomes a concrete star algebra. But it's also interesting to try to multiply these objects with themselves in this product, and we get this relation which is very close. It reminds the relation of the Weil operator. There is a slightly difference that here we have not only the antisymmetric part of the two-point function, we have also the symmetric part which plays a role, and this is essentially because in this representation, this Weil operator are not unitary operator, are unitary operator normalized, also divided by the expectation values in the state. So up to our little normalization, this is the standard relation you have among the Weil operators. So but the normalization is
the interaction equal to zero. You should get if you put the interaction equal.
No, if you put if you multiply this object by the expectation value of the ordinary Weil operator, you get the standard relation.
Okay.
It's just a little redefinition. Only because we want to work with normal ordered fields as usual, not with free fields, and so this is the normal ordered version of the standard Weil relation. Okay, but now let's start to make this comment. It's important to have this normal ordered Weil relation because eventually we would like to have a similar relation for the vertex operator, not only for the Weil operator, but for the vertex one. And if you naively try to take this object and plug in this formula, you could get divergences. Actually, here there is an exponential of the two-point function, and if this field depends on the point, and the exponential is taken before the smearing. So this is product of distribution could be problematic. If you plug in an H bar in front of this W, this object makes always sense in the sense at all order, but to be able to sum these all orders requires a regularization. Or you can try to do the same analysis in 2 dimensions for this parameter alpha smaller than 4 pi square something, I don't remember the exact number. And even in that case, it is possible. But to go into 3 and 4 dimensions, we need a regularization. So essentially, this is the reason for this extra mean field cutoff we are inserting into the game. Because we want our Lagrangian to be a linear combination of vertex operator with an integral, but we want to work with similar formulas, but at the same time, we need to have things under control. Okay, so let me try to explain what's the role of this cutoff a bit more. And we have understood that this is for, at least for field. This means simply that we have to integrate, to smear in a certain sense, to blur a little bit the field before, the field configuration before applying it into the functional. And it is quite nice that this procedure can be understood as a homomorphism of algebras. And this is very useful because then we can shift this cutoff from the field to the two-point function, and then we can play with the two-point function themselves. And furthermore, now maybe it becomes a little bit clearer why we used only this spatial integration and not the temporal one, although this integration breaks Lorentz covariance because there is a preferred choice of time in this game. Nevertheless, the time-ordered product constructed after this smearing agrees with the time-ordered product constructed before the smearing and then smearing. So the smearing and the time ordering commutes. That's the important observation. Okay, but let's try now to work inside of this object, consider the time ordering here, which, as I said, agrees with the time ordering there. And now if we take vertex operator of the form written above, products of this vertex operator becomes well-defined thanks to this smearing. Okay. Okay. And now I can give you another bit of flavor of how this convergence can be proved in this way. So at some point, I would like to compute time-ordered product of this vertex operator because these are the building blocks of our interaction Lagrangian. And now, if we do this integration with this product, we can expand it in this form. And here we have the regularized time-ordered two-point function, which is the regularized Feynman propagator of the theory. Regularized means smeared or convoluted with this cutoff function. And now this formula seems a bit ugly, but actually is not so ugly because if we want to compute expectation value, we come to evaluate absolute value of this object for generic field configuration. We immediately realize that the field configuration appear as a phase, so they can be removed into our estimate. We also observe that the regularized time-ordered product can be again decomposed into two parts, one real symmetric part, which is essentially the one you have in the two-point function of the theory, and one imaginary part, which is constructed with the regularized advanced and retarded fundamental solution of the free theory. But this is again imaginary, so this is again a phase. So if we want to compute absolute value, this part is not there. So eventually, a time-ordered product against these vertex operators mirrored locally with this G1 and G2 can be satisfied a bound of this form. And now the thing we have here at the right-hand side is not so crazy because this is nothing but a partition function of a gas of particle with charge AI, n particles, charge AI, and this WS looks like the potential of the interaction among these two particles. This G is nothing but the spatial cutoff, the spatial box where our particles are confined. So essentially, we can use techniques of quantum statistical mechanics to estimate these objects. Okay, now let's try to do a naive estimate. So let's try to say we have regularized this W. So this has become some bounded object, but here there is a sum, no? And you remember we have an exponential of this W that we need to compute. And so if we try to compute exponential here, there is a double sum at order n. We have here an exponential which goes as n times n divided by something. So not good enough. Nevertheless, this WS is not so bad because it's actually coming from a two-point function of a quantum field theory. So it's the symmetric part of the two-point function of a quantum field theory. It must be positive as a product. So we can use the positivity of this, and here we can complete a square. And so we have a square here plus a correction, which is of this form, which essentially are the diagonal element you have in this square. And the nice thing is that the sum over the diagonal element scales like n now, not like n squared. And so we get a bound for this product, which is very simple of this form. Of course, here we see that when we remove the cutoffs we have inserted into our game, the bound we have for this 2-point function diverges. So this bound works only for the regularized theory. Nevertheless, we try to construct S matrices for the regularized theories. Okay, and now maybe it's a bit more clear how does this theorem of convergence of this S matrix works. So we have this regularized interaction Lagrangian. We use the regularized propagator essentially. And then if the Fourier transform of our Lagrangian satisfy a certain bound, so this integral is bounded in a certain sense, and if this lambda 1 written above was sufficiently small, this is always the case, so this always works, then essentially we have a bound for our S matrix. And so somehow this bound shows that this S matrix converges uniformly on the field configuration, as anticipated a few minutes ago. But let's go ahead. Let's try to give ideas of how to prove this object. So we have our Lagrangians, regularized Lagrangian. We compute time ordering of these objects. These are element of this form. And then here we have the time ordered product of our vertex operator. I have already shown you how to bound these objects. So just plug in the bounds and integrate and you get your nice result. So this first part, the fourth point of these 4 points is achieved in this way. And in order to get this point, let's stress this, it was crucial to have access to the product of this regularized vertex operator. And there is already a sum in this product. So this was the key point in order to get this one. Okay, some remarks about this result. So this factor we have there, which blows up when when we remove the cutoff, is there because of normal ordering. Without normal ordering, the theory has no sense, so we cannot really remove. Nevertheless, we can now make some comment. This S of V satisfies some axiomatic properties which are very close to the one we have seen in this abstract work of Buchholz and Fredenhagen. For example, they are unitary elements, so this is very important. They satisfy the causal factorization property, at least along the time direction. So if we have a preferred notion of time, if we separate things in time, we really have this causal factorization, and the Schwinger-Dyson equation holds also in the sense of the mean field theory. Nevertheless, this kind of methods permits to construct the generating function of the correlation function essentially in the same way. And furthermore, it's important to notice that the method we use do not really use properties or strong properties of the Minkowski spacetime. So they work essentially in every background, provided you choose one state, one 2-point function, which is of Hadamard form. So very mild requirement. Okay, let me now try to move on. Next step is how can we turn this convergence at the level of functional into a convergence to unitary operator on our Fock space associated to the Minkowski vacuum. And so the idea is this one. Essentially, we use some density argument. And actually, we observe that up to a normalization, we can, if we use this Weil operator up to a normalization, essentially we get a dense set in our Fock space if we can use all the possible H bar. And so the idea is now this one. Let's plug in the partial sums into this in front of a generic element of this dense set and try to compute the norm in these objects. And essentially, since these are unitary element, what happens is that this unitary element do not really play a role in the estimate for the convergence of the series. And so with little tricks, one can show that this sum, so there is a sum missing here, I apologize. So the sum here is controlled by the sum of the original theory we have. So somehow this is potentially established by the same kind of estimate. Okay, and now in the last 5 minutes, if I am not wrong, in the last 5 minutes, I'll try to discuss how to make this construction compatible with perturbation theory. We have seen that once we have all this unitary, by abstract argument, we can extract these convergence subsequences. Now we want to do it in such a way that it is compatible with perturbation theory. And so we have to go back to a bit slightly more careful analysis of the lambda phi to the 4 in a 3-dimensional theory. And some sense, we need to check what are the Feynman diagram in the game, which are divergent. So you know this time-ordered exponential are expanded as a sum over Feynman diagrams. Some of them are divergent, so require regularization. Some of them go through without regularization. And in 3-dimensional, for lambda phi to the 4, we are particularly lucky because the divergent Feynman diagram, the one which are problematic, are just 3. So we have only 3. And the one which are problematic has this G1, G2, and G3. So this G1 has 2 external points. So essentially, it is this distribution written here, where there are 2 fields attached to the external point. There are these other 2 which have no external point. And another observation is that this is of order 2 in the interaction Lagrangian, because you need to have 2 interaction Lagrangian to build one of these. This is also of order 2, and this is of order 3 in the interaction Lagrangian. When the cutoffs are added, no problem in computing them. The problem is in computing the limit where this lambda goes to 0. People have already understood how to deal with these divergences, and one of the possible methods to deal with them is the BPH method, and Lyubov, Parachute, and Zimmerman, so very old one. And so we try to copy to get result from them and to see how does the interaction Lagrangian needs to be constructed also in this case. And so in this case, we know that we need to add some counter term, some contribution into our interaction Lagrangian. And if we do this in this way, this delta M and this C constructed in this way, then essentially, if we remove all the cutoff and if we try to up to the infrared one, if we remove all the cutoff, we get fine distribution which are well at all order in perturbation theory. So perturbation theory is renormalization of perturbation theory is recovered by these subtractions. Okay, and so now the idea is that we do the same with our cutoffs. So we add these counter terms and we compare what happens in the limits where the cutoff are removed with our sequences of unitary operator we have obtained before. And now the idea is this one. The interaction Lagrangian itself is expanded into 3 contribution, one which is linear in the interaction parameter in the lambda, one is quadratic and one is cubic, and up to rearranging of the theory if we consider the order n in this coupling parameter there. It happens that if we take for the order n, the limit where the cutoffs goes to 0, we exactly get the BPH that construction of the theory, if we use this Lagrangian there. And so now this is essentially the result. And the idea is that if instead of taking, if instead of taking this limit at fixed n, we somehow, first of all, we sum the theory and we do the same limit, we can obtain a sort of convergent sequence which agrees with the result of perturbation theory at all order in perturbation. I think that, sorry for being a bit fast here, I think that my time is essentially over, so I just want to summarize what I have said you. So taming or regularizing the interaction Lagrangian in the UV and in the adiabatic, adding adiabatic cutoff, removing large values of the fields, permit to obtain convergent S matrices. Unitarity is maintained by these procedures, something that you don't have in the Euclidean theory, but you have in this Lorentzian theory, so it's works quite nicely in the case of because then you can work with unitary operator. There are, of course, many open problems. For example, the last step, the one where you want to remove the cutoffs, it's only done essentially by abstract argument. You lose, you have existence of limit point, but you lose uniqueness. Nevertheless, you can have this weak notion of uniqueness because you make things agree with perturbation theory, but this should be improved. And then we have not discussed anything about the triviality issues you have in higher dimension in this game. And maybe to have more control on what happens, one should improve, one should employ, one should use some renormalization group technique to remove this cutoff. In any case, thanks a lot for your attention.
Any question in the comment?